Some points are worth noting about the property of velocity and acceleration vectors. The velocity vector has a point of action. It's not a sliding vector. I can't move it along a linear straight axis without a change of time parameter. T. This is the time scalar parameter. The modulus or length invariant has been parameterized by t equal 1, as it showed at the picture. Length invariant. Although the parameterization can be changed, but in the future examples, t equal 1 for all vectors. T equal 1 for all vectors. The same thing is relevant to the case of direction. Velocity integral is the area under the line that expressed the distance. The distance is equal the area. The velocity vector can be represented in contravariant component for polar coordinate systems. A few words about the velocity vectors. When additive sum must be agreed with direction. Examples I paint on the board. The acceleration vector is the operator that to do at the velocity vector. It has a point of action too. The acceleration vector shows how to quickly to change direction and invariant of the velocity vector. Of course, the acceleration vector can be represented in covariant component. But why acceleration vector is covector? The answer on this question we know later, while I take it on trust, because representation vector value are covariant and contravariant components. The acceleration integral is the area under the line that expresses the invariant of velocity. The square is equal the invariant of velocity. Always remember about that difference between t1 and t2 is equal t equal 1. In this general case, the integration of a vector is operation using scalar values. The operation of acceleration to velocity vector is defined by interval of action. The interval of action occurs in two cases. In first case, I have a Lie bracket. That method helps to search the commutator of vector field A and V. The Lie bracket is good partner for direction, but it's difficult to understand of changing invariant. In second case, I have the Lagrange function. That method helps to search current of invariant from one vector to another vector. Lagrange function is a good partner for modulus, but difficult to understand of changing direction. If the Lagrange function exists, then the space is cut on simplex automatically. The same way as I can say that Lagrange function with Euler-Lagrange equation is the pump of invariant vectors. This event expresses at interval of action. It gives understanding how the one vector to turn into another vector. Later, if necessary, it performs the contravariant summation with metrical tensor and to get the square of modulus. In this example, the direction gets from contravariant summation, but it's a trivial case because the acceleration was covariantly constant field. My idea consists of the combination two methods, Lie bracket and the Lagrange function.